Hello, ladies and gentlemen, again. I don't know where I am today. Uh, and I'm going to talk today about more trigonometric substitutions. I'm sure you love this topic by now. Um, it is incredibly isolating not knowing who is there behind the screen listening to these videos. So I think I'm going to very soon have a class meeting which is live to find out how we can improve things. Let me get started now. So with more trigonometric substitutions. Okay, so we are in the middle of section 7.3. And I'm just going to recall that there are three substitutions. There are the substitutions that correspond to a squared minus x squared, and that substitution would be x equals a sine theta. And then there's a squared plus x squared in a square root. That would be x equals a tangent theta. And then lastly, there's the x squared minus a squared substitution, x equals a secant of theta. These are the three basic substitutions, and they enable us typically to get rid of the square root in the integrand. So let's start off with an example. The integral of 1 over x squared times the square root of 1 plus x squared dx. All right, so what is the substitution? The substitution in this case, I'll do it up here, is x equals, a here is going to be 1 because there's a 1 in the square root. So x equals tangent theta, dx equals secant square theta d theta. And so we are going to substitute every term. So dx is over here, so that's secant squared theta d theta. And then the bottom is x squared, that's tangent squared theta. And then in the square root, we get 1 plus tangent squared theta. And that is simplifiable to secant squared theta d theta over, so the 1 plus tangent squared theta is secant squared theta, so it becomes, and then the square root gives you a secant theta, so you get a tangent theta times a secant theta appearing. Okay, so it simplifies to the integral of secant theta d theta over tangent theta. And this, now I think the way to go about doing this is just to return everything into sines and cosines. So it's 1 over cosine of theta over sine theta over cosine of theta, and d theta. Did I get that right? Oop, I messed up. There is a tangent. I got to go back. Mistake. I did not copy over this tangent squared theta. So there's a tangent squared theta here. So there's a tangent squared theta here. And so let me correct for this. Okay, so where we get 1 over cosine of theta, that's the secant theta term, and then there's sine squared theta over cosine squared theta on the bottom, which then becomes, if you work it out, the integral of cosine theta over sine squared theta d theta. And this is okay. Now, the way to finish this off is to let u equal sine theta. We're going to do an ordinary substitution, then du is cosine of theta d theta. And that will give me an integral of du over u squared, which is u to the minus 2. So you get minus u to the minus 1, or minus 1 over u plus c. Now the rest of the problem is to convert back to the original variable x. So it has to go in 2 steps. We know that u is sine theta, so it's minus 1 over sine theta plus c. Okay, and or if you like, minus cosecant theta plus c, if you like, if you want to do it that way. So now I draw a right triangle. And we know that x is tangent theta, so if theta is the angle here, it's a right triangle. Opposite over adjacent has to be x, so if we use x there, we get a 1 there. The hypotenuse is 1 plus square root of 1 plus x squared. Then the cosecant of theta is given by the hypotenuse over the opposite, so it's the square root of 1 plus x squared over x plus c. And that is the final answer to this first example. Okay, very good. Okay, so for my next example, example 3, I'm going to consider the following expression: dx over the square root of x squared minus 4. So remember, this is of the type x squared minus a squared. So we're going to let x be equal to 2 secant of theta. So then dx is 2 secant theta tangent theta d theta. And we substitute, we get 2 secant theta tangent of theta d theta over the square root. Okay, so what is the square root of x squared minus a squared? Well, that's the square root of 4 secant squared theta minus 4, which is, you can pull the 4 out, you'll get a 2 through the square root, and then you're left with secant squared minus 1, which is tangent theta. So on the bottom is 2 tangent theta. So we get cancellation everywhere. And we finally obtain the integral of secant theta d theta. Oops, let me simplify my life a little bit. Now we've computed the integral of secant theta already, and let's recall that it's ln absolute value of secant theta plus tangent theta plus c. So now we have to go back to the original substitution we made. So secant theta is x over 2, according to that, because if we put theta in the right triangle, secant theta is hypotenuse over adjacent. So, because it's 1 over cosine. So therefore, secant theta is x over 2. So if we let x be the hypotenuse, 2 must be the adjacent, and then the opposite is the square root of x squared minus 4. Okay, so now we can now compute all the terms, because ln of secant theta, well, secant theta is x over 2, and tangent theta, and there's an absolute value, tangent theta is opposite over adjacent, so that's the square root of x squared minus 4 over 2 plus c. So that is the solution to this problem. It wasn't that hard. So let's move to the next problem. So what's that? Okay, now we get to more complicated expressions. So let me try something like this. The integral of dx over the square root of 9 minus 4x squared. So the idea in this one is to make it look like, this looks something like the square root of a squared minus x squared, but it's not exactly in that form. The idea will be to consider this as 9 minus 2x quantity squared, which is the same thing. So therefore, what we can do is, this suggests the case where a is 3, and we should let 2x, we think of 2x as like as x instead of x, and 2x will be a sine theta, which is 3 sine theta. That should be the substitution there. So this is what we're going to use as the substitution. And then, so then what is, we can think of this as x is 3 halves sine of theta. So dx is 3 halves cosine of theta. So that's d theta. Okay, so that the substitution will be that. And if we do it, we get 3 halves cosine theta d theta. And what is a squared minus x squared going to be? It's going to be the square root of a squared. What is a squared minus x squared in this case? Is 9 minus 2x quantity squared, which is 9 minus 9 sine squared theta, which is 9 times cosine squared theta. So that's going to be in the square root. So that's going to give me a 3 cosine theta on the bottom, a 3 cosine theta on the bottom of the integral. So therefore, this is the integral of what? 3 halves divided by 3. It's going to be 3 halves divided by 3, which is 1/2 d theta. The cosine thetas cancel. I think that's right. Okay. So so good. And then this is going to be 1/2 theta plus c. And then we have to figure out what theta is. Well, what is theta? Well, 2x equals 3 sine theta, so 2/3 x equals sine theta. So theta is equal to the inverse sine of 2/3 x. So the final answer is 1/2 arc sine 2/3 x plus c. Assuming I haven't made any arithmetic errors. That is the solution. Okay. So we move on to one last problem for today. Let me write it out. So this is, I think this is my fifth example today. The integral of dx, and this is the end of the section, by the way, over the square root of x squared plus 2x plus 5. Okay, so what do we do there? So now the problem is that this is not in the correct format. It's x squared plus 2x plus 5. There's no first power of x in our substitutions that we're allowed to do here. So the idea here is to complete the square. So x squared plus 2x plus 5 is x squared plus 2x plus 1 plus 4, which is x plus 1 quantity squared plus 4. So I'm going to rewrite this in the opposite way as 4 plus x plus 1 quantity squared. So this would be the integral of dx over the square root of 4 plus x plus 1 squared. And this is looking like a square root of a squared plus x squared type problem. So, but instead of x, we have an x plus 1. So we should let x plus 1 equal 4 as the square of a. So 2 tangent theta should be the correct substitution. And then dx is 2 secant square theta d theta. And then we make the substitution. So the numerator is 2 secant square theta d theta. And we're going to get on the bottom, after plugging in the 2 tangent theta, it's going to be the square root of 4 plus tangent squared theta, which is going to be 4 tangent squared theta. So that's going to be a 2 secant theta popping out. Okay, and that's this cancellation. We get the integral of secant theta d theta, which we've already seen was ln of secant theta plus tangent theta plus c. So finally, we need to convert this back to x notation to the x variable. So we know that x plus 1 is 2 tangent theta, so x plus 1 over 2 is tangent theta. So the hypotenuse would be the sum of the squares, which turns out to be the original expression in the square root we had, x squared plus 2x plus 5. So we're now able to write the answer in terms of x. Secant theta is the square root of x squared plus 2x plus 5 over 2 plus tangent theta. And this is all absolute values I should write. So let me put a straight line here. Tangent theta is opposite over adjacent, so that's x plus 1 over 2 plus c. And there you go. And we're now done with trigonometric substitutions for now. So that's great. I'm really happy. I think that we've worked hard enough today, and maybe it's time for a worksheet. That'll probably be our next lecture. Okay, take care. Cheers. Have a good day.